I've just described to you the hypar with straight edges, the umbrellas, and all the derivative of the umbrellas. Let's go back now to the hypar with curved edges, which was essentially his first hypar design, the Cosmic Rays Laboratory. This design, while it was very important for Candela, it elevated him to a level of international recognition. It left him a bit unsatisfied. He wanted to know or figure out how you can design a shell structure with curved edges that wouldn't have to be continuously supported on the side, as was Cosmic Rays. For example, how did he get from Cosmic Rays to the restaurant Xochimilco? What was that evolution of thought? He began working on this idea of the free edge with a project called Bolsa de Valores, which was essentially the stock exchange hall completed in 1955. It took Candela about a year to figure out how to do it. And in the simplest terms, the way you can describe the shape of this groined vault is that you take two saddles at 90 degrees to one another and you intersect them. And at those points of intersections, you get the valleys of this groined vault. For Bolsa de Valores, the first project where he designed a project of this shape, he had to use pretty large beams on the edge of the shell, which disguised the thinness of the shell itself. But for his next large project, San Antonio de las Huertas Church in 1956, we see the shell under construction freestanding without those heavy beams on the edge. So how do these groin vaults work? Well, basically what Candela does is he increases the thickness of the concrete from 4 centimeters to 12 centimeters, right at that valley, right where the two shells come together. And at that peak of that valley, at that point of that V, he embeds rebar or reinforcement, steel reinforcement, to carry the loads of the shell. At point B, which is the crown of the shell, we have essentially the top of this valley, and at point A, we have the foundation. The blue arrows represent the loads that are being carried from the 4 centimeter thick shell into that valley, into that thickened concrete segment. In the end, that valley in these groin vaults behaves as a 3-hinged arch, and I'll describe that better as I come to our next project that I'll describe, Restaurant Los Manantiales in Xochimilco, completed in 1958. When I first started studying this restaurant, I couldn't see the hypar in this design. I saw a lot of curves, but I couldn't see the straight line generators, and it took me a while to understand that. But basically, we have a series of straight line generators, a series of intersecting hyperbolic paraboloids. The best way to explain it to you is to look at an animation. The straight line generators for Xochimilco are at 60 degrees to one another. And in this animation, we see a very warped surface with curvature in 2 directions. Now we're going to see this single warped surface being cut up a little bit. And as we make those cuts, we're going to start to see the shape of Xochimilco. So in the first cut, in the center, is what forms the crown of the shell, the center, the very top. And in the next cut, we see the parabolas that are formed, which form essentially that space where the glass is to enclose the restaurant. And if we copy now the shape that remains 3 more times over, we see the full shape of Restaurant Los Manantiales in Xochimilco. When we examine the images of this restaurant under construction, we see those straight line generators through the straight pieces of wood, the boards that form the shape. We also see under construction that on top of that wood, once they're spaced closely together, we have steel reinforcement. There's a grid of 3/8 inch diameter steel reinforcement in 2 directions, which is always necessary for concrete to control the creep and shrinkage effects. Once the wood and the steel reinforcement is in place, then the concrete is placed on top of that. This concrete is essentially a very dry mix because these are very steep surfaces, and at that time, late 50s in Mexico, the way it was placed was 1 bucket at a time. An aerial view of the restaurant, we see that surrounding this restaurant is a canal with gondolas. So it's a popular place for people to go spend time on the gondolas with friends and family. As I mentioned earlier, the way to analyze this groin vault is thinking of it as a three-hinged arch. This is part of the simpler calculations that Candela made to understand the forces that flow through it and how to design, in particular, that valley, the place where these shells intersect. So at the very top, at the crown of the shell, you have a hinge, and at the supports, you have hinges as well, so that's 3 hinges. And the shaded portion of that shell is the load tributary to that arch. It's the load that's being dumped on that arch, the arch representing the valley of the shell. Candela was very proud of the support conditions of this shell. Instead of coming down to a very pointed V condition, he makes a nice rounded U, which integrates with the rest of the shape of the shell. Unfortunately today, this detail of the support is no longer visible. There's a trough there, so you can no longer see the very delicate way that the shell touches the ground. And also there's a fence to prevent people from climbing on top of the shell. But in the name of research, we were able to get permission to climb that shell and go to the top and inspect the shell. In what condition is this shell? This is, again, designed in 1958, so how does it look today? And from the very top, we see different colors. That coloration is just representing different colors of waterproofing. Initially, it was a red waterproofing and then a white. And we see there has been some maintenance on these shell structures, which is common to all concrete structures. There is some maintenance required. But the maintenance hasn't been extreme. It's been a normal level of maintenance. As far as I can tell, the shell is in excellent shape. There is no significant damage to it, and it's been well maintained. From the inside, we see again the imprint of that formwork that was used to generate this very curvilinear surface, indicating again the hyperbolic paraboloid form. The inside space can be used for an assembly or a conference. It also is used as a restaurant and as a place to dance and have fun. Chapalomas de Cuernavaca, completed in 1959, is probably the largest saddle-shaped structure, at least the largest that I know of. So it's one single saddle shape. And the way it is generated, it's again the hyperbolic paraboloid. This time the generators are at 90 degrees to one another, as shown in the sketch. If we look at an image of this structure under construction, we see those straight line generators forming the shape that needs to be taken for the concrete to be then poured. Let's look at an animation of this structure to give you an idea again of how we come from straight line generators at 90 degrees to the shape of the large saddle for Cuernavaca. We begin with what looks like a flat sheet, something flat, but with a different perspective, we see it's actually a warped surface, a hyperbolic paraboloid generated with 2 lines of generation at 90 degrees to one another. In the first cut, we see the hyperboloid that forms the foundation for Cuernavaca, and in the second cut, we see the parabola that forms the entrance to the church. So by taking cuts to the single warped surface, we're able to arrive at the shape of Cuernavaca. Once the straight pieces of wood are placed on in the straight line generation so that they're one right next to another, and then the steel is placed, then the concrete is placed, again this dry mix concrete, and then we wait till the concrete hardens. At that point, this wooden scaffolding, this wooden formwork needs to be lowered, and it needs to be lowered very carefully so as to not induce any kind of bending moments in that shell. Any error in construction can cause the shell to collapse, and this is true not only for Cuernavaca but for any shell construction. In this case, indeed, there was an error and the shell did collapse when that formwork was being lowered. There was a study done here at Princeton, also as well at the University in Mexico independently, and we both came to the conclusion that the collapse of the first design of Cuernavaca was due to a construction error. The reason that we came to that conclusion is that the original design by Candela, which was taller than the one that stands there today, was a design that could have withstood the forces and the loads, not only of its self-weight, but wind as well. So the design was fine. In other words, there was no reason why that design couldn't have stood, and we verified this through very modern tools that are available to us today that were not available to Candela back in the 50s. Therefore, both of us at the University of Mexico and at Princeton came to the conclusion that the error must have been in the construction.